Most of part 2 is going to be the derivatives of e's, ln's, and then the word problem. To do the derivative of an e, the derivative of an e is its coefficient, if the coefficient is a constant, times the derivative of the exponent times the e function unchanged, the e part of the function without any tweaking. So in problem 11, if I want to insist on the coefficient, it's a 1. I don't need to include the 1 in my computation, but I can. So the derivative, it's going to be the coefficient of 1 times the derivative of the exponent, and the exponent is x squared. The derivative of x squared is just 2x. So it's the original function, 1, times the derivative of the exponent, times the e function without any changes to it. So just e to the x squared. I don't subtract exponents for e's. And this 1 times 2x is just 2x. Insisting on the coefficient of 1 made me have to do an extra step here. But it's fine. But you don't need to put the coefficient of 1 if it's part of the problem. If it's not part of the problem. Question 12 is multiplication, and both factors have a variable. So I need to use the product rule. I need to put the first factor, which is 2y minus 4, and the second factor, e to the 5y squared, in some sort of table. I usually don't get so formal with my table, but since it's easy on a computer, I can make a nice table. And then underneath I'll write its derivative. The derivative of 2y minus 4 is 4. And to find the derivative of e to the 5y squared, and again it's 1 times e to the 5y squared, it's going to be the coefficient of 1, that's not necessary, times the derivative of the exponent. I wrote d dy because the exponent has a y, so times the derivative of 5y squared. The derivative of 5y squared is just 10y. Multiply the 2 times the 5 and lower the exponent by 1, and then times the original e function, which is e to the 5y squared. So this derivative is going to be 1 times 10y, or 10y, times e to the 5y squared. Now I'm ready to use the product rule. Cross multiply, put a plus between. So my derivative, f prime of y, equals this multiplication. I'm going to need to put this 2y minus 4 in a parentheses because it's a binomial, and get 10y times e to the 5y squared times 2y minus 4, and then multiply that way and put a plus sign between, plus 2 times e to the 5y squared. I'm going to do a double factoring for this. I'm going to factor out between the 10 and the 2, I'm going to factor out a 2, and I'm also going to factor out the e to the 5y squared. So rather than taking 3 steps to do the factoring or 2 steps to do the factoring, I'm going to do it all in once. So first I'm going to factor out a 2 between the 10 and the 2, and then I'm going to factor out an e to the 5y squared. Write my parentheses. This 10 turns into a 5 when I factor out a 2. I go 10 divided by 2 is 5. I still have this y, still have this 2y minus 4 to the left of my plus sign. After my plus sign, I'm just going to get a 1 because I factored it out completely. Just need to clean up this parentheses to get my answer. To clean up this parentheses, I'm going to do 5y times 2y and get 10y squared. I'm going to do 5y times minus 4 and get minus 20y. And I'm just going to write that second parentheses with all 3 terms. So my common factor comes first of 2 times e to the 5y squared. And then my second parenthesis simplifies to 10y squared minus 20y plus 1. That's prime, but I wouldn't even try to factor a trinomial like that for us. So that's good for number 12. 13 is dividing, and I can't get rid of it. I probably could get rid of it and rewrite it because of the monomial, but that'd be crazy to do. So I see a division, I'm going to use the quotient rule. I'm going to write down the denominator and the numerator, and then take the derivative of each. For the derivative of e to the t, or 1e to the t, it's going to be the coefficient of 1 that's not necessary times the derivative of the exponent, and the exponent is just a t to the first power, so its derivative, since it's a first power, it's just its coefficient. Its coefficient is 1, so the derivative of t is just 1 times the e part. And the e part is still e to the t. So this derivative is 1 times 1, or 1e to the t, which is just e to the t. It's its own derivative. For the t to the fourth, its derivative is 4t cubed. Now I'm going to cross multiply, put a minus between, and make my denominator. So cross multiply, minus between, do the denominator squared. So the derivative, f prime of t equals to, when I cross multiply this way, I'd probably write it as 4t cubed times e to the t. And when I cross multiply this way, I'd probably write it as t to the fourth times e to the t, all over the denominator, which is e to the t squared. Running short on paper here, so let me pull out my common factor in one huge step. I'm going to pull out between the t cubed and the t to the fourth, I'm going to factor out a t cubed. And between this e to the t and that e to the t, I'm going to factor out an e to the t. I'm going to rewrite the denominator with e to the t written twice rather than the exponent of 2. In the numerator, when I factor out the t cubed to the left of the minus sign, it's gone. When I factor out the e to the t from the left of the minus sign, it's gone. I'm only left with a 4 to the left of the minus sign. After the minus sign, there was a t to the fourth. I factored out 3 of those, so I'm left with a t to the first. And I took the e to the t all the way away. Now I can cancel out this e to the t with that e to the t and get something that's completely suitable as an answer. I can say the derivative is t cubed times 4 minus t over e to the t. If that bugs you, seeing the t written second in the parentheses, you can rewrite it as t cubed times negative t plus 4 over e to the t. And then if you take the time to write it that way, you're going to factor out a negative 1 from this parentheses and put it in front of the t cubed. And when I factor out a negative 1 from a parentheses, the negatives turn positive, the positive turns negative. This negative t would turn to a positive t when I factored out a negative 1. This positive 4 would turn to a negative 4 when I factored out a negative 1. This is where I'd probably instinctively leave my key. This is equally good, and I wrote both of these over here, although I suppressed the 1 and just wrote a negative sign. But both perfectly correct answers. But you don't have to go through and write with the t first and factor out a negative unless you just like that. For 14, it's the derivative of an ln. And for the derivative of an ln, you get the coefficient, if there's a coefficient, times the derivative of the argument over the argument. The derivative of an ln doesn't have an ln. It's a fraction, and in the numerator of the fraction, it's any coefficient that doesn't have a letter. In this case, it's a 1. I don't need to really write it. So really, the derivative of this is just the derivative of the argument divided by the argument. So let me write that down. The derivative, f prime of t, is going to be a fraction. In the denominator, it's just the argument of 3t to the fifth. In the numerator, it's derivative of that argument, so the derivative of 3t to the 5th, which is 5 times 3, which is 15, and then lower the exponent by 1 and get t to the 4th. The 5 over 3 is going to reduce to 5, so this is going to be 5t to the 4th over 1t to the 5th, and I can cancel all of the t's from the t to the 4th with 4 of the 5 t's from the t to the 5th. And for a derivative, I'm just going to get 5 over t. Problem 15 has an ln, but it has multiplication and both factors have an x, so I need to use the product rule. I need to separate the first factor of x squared from the last factor of ln of x, take the derivative of the first factor, which is 2x, take the derivative of the second factor, and when I go to do the derivative of the ln of x, I'm going to get a fraction. In the numerator would first be the coefficient, but there's no coefficient, I don't need to write it. In the numerator, it's the derivative of the argument, and in the denominator, it's just the argument itself. So I take the argument, put it in the denominator, the derivative of that argument goes in the numerator, and this x, because it's a first power term, its derivative is just its coefficient, and its coefficient's the implied 1 that's not written, but it's assumed. So the derivative of ln of x is just 1 over x. Now I'm going to cross multiply, put a plus between. So I'm going to say y prime, which is the lazy version of writing the symbol for the derivative, is x squared times 1 over x plus 2x ln of x. This fraction cancels. This x cancels out one of the x's from the x squared, leaving me with a single x. So for this multiplication, I'm just up with x times 1 because I have 2 x's kind of over 1x. I could cancel out one of the x's. My first term is going to be x times 1, which is just x. My last term is 2x ln of x. This is an acceptable answer, but there's a common factor of x that I probably should factor out. This is a better answer. If I factor out an x, I'm left with 1 plus 2 ln of x. And if it bugs you that the x is written second, this is also an acceptable answer, writing x times 2 ln of x plus 1. That's probably the nicest answer, fully factored, written with the x first in the parentheses, but any one of those on a test would get you full credit. 16 is another horizontal tangent line, so second one on this review's got to be one on the test. To do 16a, to find the values of x where the tangent line is horizontal, we find the derivative, and then we solve the derivative equal to 0. So to find the derivative, to do the derivative of e to the x squared, it's the coefficient, which is 1, so I don't need it. It's just the derivative of the exponent times the e part unchanged. The derivative of the exponent, the derivative of x squared, is 2x. The e part unchanged is the e part unchanged. So I found the derivative. I have f prime of x equals 2x e to the x squared. Now I'm going to set the derivative equal to 0. Go 2x e to the x squared equal to 0. It's factored, so I split this in half and go 2x equal to 0 and e to the x squared equal to 0. For the 2x equal to 0, I just divide both sides by 2, and this is going to give me x equal to 0. And e to some power can never be 0. This is going to have a no solution. So the only answer to part A is x equal to 0. For 16b, I have the x coordinate of a point from the algebra in part A. By default, because I'm looking for a horizontal line, the slope is 0 because all horizontal lines have slopes of 0. I need to get the y coordinate of the point, and I get the y-coordinate of the point by using the original function and not the derivative. Plugging numbers into derivatives gives me slopes. Plugging numbers into the original function gives me the y-coordinates of points. So if I just change that x to 0, I get e to the 0 squared, which is e to the 0, and anything to the 0 power is 1. So the y-coordinate of the point is 1. And now I can just go y minus the y-coordinate of the point equals m times x minus the x-coordinate of the point, which is going to be y minus 1, the y-coordinate of the point, equals m, which is 0, times x minus the x-coordinate of the point, which is 0. The right-hand side comes out to 0 because anything times 0 is 0, even if it's multiplied by a binomial. I'll add 1 to both sides and get y equal to 1 for my answer to part B. One last problem, it's the word problem. Actually, two last problems, 2 word problems, but they're the same kind of problem. So, question 17 gives me a cost function to make supersized candy bars. And it says the cost to make x supersized candy bars is given by the formula ln of x plus 0.15x. First it says find C of 4. To do C of 4, I'm just going to plug 4 into the original function. And this is going to give me the cost to produce that many candy bars, in this case 4 candy bars. I need to round to 2 decimals, definitely, because costs are money, and money has just 2 decimals once for change. So I do the ln of 4 plus 0.15 times 4, and I get 1.986. I'm going to round that to $1.99. So for my answer to C of 4, I just wrote $1.99 down here without any explanation, without even the dollar sign. It's just a number at this point. When I go to interpret my answer, because C represents the total cost to make X candy bars, I'm going to say for part B, it will cost $1.99 to make 4 of these supersized candy bars, so about 50 cents each. Part B wants me to find the derivative. And I think I found the derivative of ln of x for the last few problems ago. So to find the derivative, I need to find the derivative of ln of x. I did that a few problems ago. The derivative of ln of x is just 1 over x. Because to do the derivative of ln of x, you find the derivative of the argument, put that in the numerator, and put the argument in the denominator. The derivative of x, because it's a first power term, is just its coefficient, and then the denominator is x. So the derivative of ln of x is 1 over x, and the derivative of 0.15x is just the coefficient of 0.15, because that's a first power term. Its derivative is its coefficient. So this is the derivative for part C. I don't need to write the 0 to the left of the decimal, but I can. It's just kind of a matter of preference. So that's the answer to part C. Now I'm going to plug 4 into this function and just get a number. So the marginal cost of 4 candy bars is 1 over 4 plus 0.15. That's just plugging in. I think that gives me 40 cents. So 1 divided by 4 plus 0.15. It's 0.4. So my answer to part D, I snuck the extra decimal in there because it was money, but I could have just put 0.4 even without the 0 preceding or without the 0 afterwards. Plugging numbers into a marginal cost function gives you the cost of making the next unit. So plugging 4 into the cost function gives me the marginal cost function, gives me the cost of making, in this case, the next unit or the 5th candy bar. So as a dollar, in a dollar notation, I just put a dollar sign next to this. It costs $0.40, which is the same as 40 cents to make the 5th candy bar. So it's important to know the difference between marginal and total. Plugging numbers into the cost function gives you the cost to make that many candy bars, in this case the cost to make 4 candy bars. Plugging the same number into the marginal cost function gives you the cost of making the next one, in this case the 5th one. Now we do the same questions just with profit as opposed to cost. And this parenthetical comment says this formula is only going to work for the first 1,000 units. In this case, we're making widgets. So a corporation determines the weekly profit P of X from selling a certain widget. I guess X is the number of widgets. X equals the number of widgets that they sell. It's not really stated so nicely, but it's, I guess, implied by the way the problem is written. So this is a profit function. If I plug numbers into it, it gives me the total profit for selling that many widgets. And let me do part A, which just involves the profit function. So for part A, I'm supposed to do P of 500. P of 500 is going to be negative 0.01 times 500 squared plus 20 times 500 minus 2,000. And I should get 5,500 if my answer is right on the bottom. So negative 0.01 times 500 squared plus 20 times 500 minus 2,000. And I get 5,500. So the algebra here just gives me a number without any interpretation. And that's what I wrote down here for an answer to 18A. That's just a number. Now I'm going to attach meaning to that number. 500 represents the number of widgets, 5,500 represents the profit, and I'll just live with that because that's better than I could probably write right now. So the profit will be $5,500, and this is a weekly profit in a week when 500 widgets are produced and sold. Actually, yes, produced and sold. For part C, it wants the marginal profit function, which is just the derivative of the profit function. So marginal profit is derivative of profit. I'm going to find it by doing the general power rule. I'm going to multiply the exponent of 2 times the coefficient of negative 0.01 for the first term, lower it from x squared to x. The second term is a first power term. Its derivative is its coefficient of 20. The last term is a constant. Its derivative is 0. So the marginal profit function, if I just do this multiplication, is negative 0.02x plus 20. That's my answer to part C. Part D wants me to plug in 500, not into the profit function, but into the marginal profit function. And I get negative 0.02 times 500 plus 20. And if I didn't make a mistake, this comes out to be 10. So negative 0.02 times 500 plus 20, that's just 10. So the answer to part D is the marginal profit function evaluated at 500 is just the number 10. And now I'm supposed to explain what that means. Marginal means next. So the company will earn, and that's how much money they'll earn by selling the next widget. So they're going to earn $10 when they sell the 501st widget. Always when I'm doing marginal, I have to add 1 to this number to put it in my answer. And this is, the dollar amount, either the cost, the revenue, or the profit, depending on what kind of function I'm working with. So that's the entire 2 parts of the review. If you can do all the problems on the review, you should always be comfortable with doing well on my tests. I usually only put 1 of these word problems. Sometimes on the Canvas practice test, I put the profit word problem, but on the test I put the cost one. So be able to do both the cost and the profit word problems. They're identical, except you're changing the word profit to cost essentially. So be comfortable, just in case on the Canvas practice test, the problem is a profit, but on the actual test it's a cost. These I think are interchangeable. I think there's only 1 on the Canvas practice test, and it didn't do both kinds of equations.